Hi to all. In the previous classes we discussed about the magnetic potential. What is magnetic potential? What are the various laws that satisfies the magnetic potential? What are the types of magnetic potential? The properties of curl, that is del dot del cross A equal to 0 and del cross del V equal to 0, where V equal to scalar, A is a vector. The two equations must satisfy the identities, vector identities. And similarly, we classified magnetic potential into scalar and scalar magnetic potential. What are the properties of scalar magnetic potential? We discussed previously. Now we go for vector magnetic potential. What is vector magnetic potential? That will go now. What is vector magnetic potential? What is the representation of vector magnetic potential? The vector magnetic potential, what is the equation? That del dot del cross A, del dot del cross A equal to 0, where A is the vector magnetic potential, where A is the vector magnetic potential. The vector magnetic potential A, it is denoted as, it is measured in Weber per meters. It is measured in Weber per meters. It has to satisfy this equation, del dot del cross A equal to 0, where A is a vector, where A is a vector. It has to satisfy this condition. It has to satisfy this condition that divergence of a curl, del dot means it is a divergence. Divergence of a curl of a vector is always 0, where A bar is known as vector magnetic potential. Let us go for vector magnetic potential in detail. The vector magnetic potential is indicated as A bar. That we have to remember. What is scalar magnetic potential is indicated as Vm. Vm, scalar magnetic potential, previously we discussed. The scalar magnetic potential, what is the unit is ampere, whereas vector magnetic potential unit is Weber per meter. How to define vector magnetic potential? We have to remember. It is defined as, it is one of whose curl of it gives magnetic flux density. One of the whose curl gives magnetic flux density. That is del cross A equal to B bar. The vector whose curl is gives magnetic flux density. Del cross A is nothing but any vector. The curl gives magnetic flux density. It is known as, where A bar is known as magnetic potential. What we are representing here is the vector A bar is a vector magnetic potential and curl of vector magnetic potential gives magnetic flux density. That we have to remember. Thus, the curl of vector magnetic potential is the flux density. That is, the definition means whose curl of gives magnetic flux density, that may be represented as vector magnetic potential. Curl of any quantity gives always a vector. Curl of a scalar is also a vector. Curl of a scalar is also a vector. That we have to remember. It is also defined as vector magnetic potential A bar, and it is approximately equal to H iodide from the Ampere circuit law. What is the magnetic flux density? What is the vector magnetic potential? Approximately equal to closed integral mu naught IDL by 4 pi r. That also equal to mu naught K ds by 4 pi r. That also equal to mu naught J dV. Mu naught J dV. Del cross H equal to J. That already you know this formula. Del cross H equal to J. Ampere circuit law. From Ampere circuit law you know this. Coming to explanation of vector magnetic potential, how to explain? For Maxwell's second equation, from Maxwell's second equation we are using explanation of vector magnetic potential. We know that Maxwell's second equation, that is del dot B equal to 0. From the Maxwell's second equation, del dot B equal to 0. From vector magnetic potential, what we know, B equal to del cross A. Already we made this equation 1. Del dot B equal to 0 from Maxwell's equation, and B bar equal to magnetic flux density equal to curl of vector magnetic potential. We know that already the relation between B and H, B equal to mu H, H bar equal to B by mu naught, we can substitute. Therefore, H bar equal to del cross A by mu naught. We can substitute here B equal to mu naught H for absolute permittivity mu naught H. Mu r equal to 1 for free space. Mu r equal to 1 for free space. We can substitute here del cross A. From this H bar equal to del cross A by mu naught. Del cross A by mu naught. Now taking the curl on both sides, del cross H equal to, taking the curl, that means del cross H equal to 1 by mu naught del cross A. Taking the curl on both sides means cross product of del cross A equal to one equation, assume that. But del cross A equal to del cross A equal to, we can substitute del dot A minus del square A square. This is due to vector identity. To express left hand side, we can write del into del dot A minus del square A square by using this formula. We have to remember this formula. Del cross A, the curl of a curl is del into del dot A minus del square A square. Substituting equation 3 in equation 2, we are substituting del cross A. In place of this, we can substitute here this one. Del cross H equal to minus 1 by mu naught del into del dot A minus del square A. Because we already know that Ampere circuital and point form, del cross H equal to J bar. Ampere circuital and point form is del cross H equal to J bar. We can substitute in place of del cross H, we can substitute J bar. J bar equal to 1 by mu naught del dot A equal to 0. We can substitute del dot A equal to 0 minus del square A. Del square Vm equal to 0. Del dot del A equal to del square A. That is, since del square Vm equal to 0, we can substitute del square A equal to 0 del square A. Therefore, del square A equal to minus mu naught J bar, where J bar is the current density. Minus mu naught J. Del square A equal to minus mu naught J bar. That means, if vector magnetic potential is known, then current density can be calculated. If you know vector magnetic potential A bar, then you can calculate J bar. Del square operation on vector magnetic potential gives rise to J bar, current density. Where J bar is not equal to 0, then only vector magnetic potential will be present. The current density need not to be 0. J bar should not equal to 0. Previously, scalar magnetic potential J bar equal to 0. That we have to remember. Thus, if vector magnetic potential is known, then current density J bar can be obtained. For defining A bar, the current density need not to be 0. That is very important. The vector magnetic potential exists when J bar is not equal to 0. Previously, scalar magnetic potential J bar equal to 0. Now we go for difference between scalar and vector magnetic potentials. Simple, if you know the scalar and vector magnetic potential basics. Previously, in previous lecture, we started a scalar magnetic potential. Now we completed a vector magnetic potential. Now the differences you can see. The same matter, again we are comparing. It is defined as whose negative gradient potential gives rise to magnetic field strength H bar. H bar equal to minus del Vm. That is where Vm is known as vector magnetic potential. It is also defined as whose curl gives magnetic flux. Curl of A bar equal to B bar. That is vector magnetic potential. Simply we are comparing. It is measured in scalar magnetic potential measured in amperes. You know that. It is measured in amperes per meter or Weber per meter. It is a scalar quantity, it is a vector quantity. The differences. It is when J bar equal to 0, then only it exists. When J bar is not equal to 0, J bar is need not to be 0, then vector magnetic potential will exist. Vector magnetic potential will exist. It is used in permanent magnet applications and magnetic circuits. We are using this one. It is used in antennas antennas near and far fields, the difference will be. In antennas we are using, in permanent magnet applications we are using scalar magnetic potential, whereas in case of antennas we are applying this vector magnetic potential. That is the difference between scalar and vector magnetic potential. Now you clearly understand that scalar and vector magnetic potential clearly. Why vector magnetic potential? Why vector magnetic potential A bar is a vector? Because simple reason, the B bar is a vector, B del cross B equal to A bar, or del cross A equal to B bar. That is the vector magnetic potential where A bar is. In the same way, the charge is producing electric field. In the same way, current carrying element produces magnetic field H bar or B bar. The B bar is a vector and hence A bar also vector. The curl of a vector or scalar is equal to vector. The curl of any quantity is a vector, hence A bar also a vector. We can say that. Now another topic, Poisson's equation. The Poisson's equation for vector magnetic field. The Poisson's equation for vector magnetic field. That is very important. Write the Poisson's equations for magnetic field. They will ask the questions like that. In vector algebra, vector can be fully defined if its curl and divergence are defined. In vectors of the algebra, you know that vector can be fully defined if its curl and divergence are defined. The Poisson's equation, simply the Poisson equation is del square A equal to minus mu naught J. Del square A, where A bar is vector magnetic potential. It is del square A equal to minus mu naught J equal to Poisson's equation for magnetostatic field. Del square A equal to minus mu naught J bar, where A bar is vector magnetic potential, J bar is known as current density. That is the Poisson's equation. Simply for 2 marks if they ask, you can write this. Del square A equal to minus mu naught J is known as Poisson's equation for vector magnetic potential or magnetic field, magnetostatic fields. But for 5 marks or 10 marks if they asked, then we have to derive this derivation. Go for derivation now. Again, from Maxwell's second law, we are going for deriving this. Maxwell's second law, del dot B equal to 0. From the definition of vector magnetic potential, del cross A equal to B, that is already we know that. From Maxwell's second law, del dot B, divergence of magnetic flux density equal to 0. From the definition of vector magnetic potential, we know that del cross A equal to B bar, that made as equation 1. We know that B equal to mu naught H already. Therefore, H bar equal to B by mu naught. Therefore, H bar equal to, we can substitute here, the H bar equal to del cross A, B equal to del cross A, we can substitute. Already previously we derived this also for scalar vector magnetic potential. Now taking curl on both sides, del cross H equal to, taking curl on both sides, that is del cross H equal to 1 by mu naught del cross A. Del cross H equal to J bar, already you know, it is point form of Ampere circuit law. Next another one, therefore J bar equal to 1 by mu naught del cross A. We can substitute here del cross A equal to, already I told you in scalar magnetic vector magnetic potential, we can substitute in place of that according to vector identity. Using vector identity to express this one, del cross A is del into del dot A minus del square A. That we are substituting here. That is J bar equal to 1 by mu naught del into del dot A minus del square A. Since del into del dot A equal to 0, divergence of divergence is 0. It is divergence of divergence becomes 0. That we have to remember. Okay, simply taking the curl on both sides. After that, we are substituted by vector identity. Del dot A we are substituted in place of this one. Del dot A equal to 0. Therefore, mu naught J bar equal to 1 by mu naught 0 minus del square A. From that, del square A equal to minus mu naught J. This is known as Poisson's equation for magnetostatic field or vector magnetic potential. Poisson's equation for magnetostatic field. Magnetostatic field, it is. This equation is del square A equal to minus mu naught J. This is the Poisson's equation for magnetostatic field, where A bar is vector magnetic potential and J bar is current density vector and mu naught is absolute permittivity. Now we go for self-inductance and mutual inductance in vector magnetic potential or scalar magnetic potential. Unit 4, self and mutual inductance is another topic. What is these are the basic concept already you studied previously. The self-inductance of a coil. What is meant by self-inductance? When a coil is supplied to positive or negative DC voltage, magnetic flux will be created because of flow of current. Due to the flow of current due to the battery, a magnetic flux will be created. The magnetic flux direction also you can give by thumb rule. Inductance of a coil is due to its own current is known as self-inductance. Self-inductance is by itself due to inductance of coil due to its own current is known as self-inductance. Consider a coil carrying a current. Suppose the coil is carrying a current, I current is flowing in this, produces a magnetic field B bar. If the coil has n number of turns, the flux linkage will be psi equal to lambda equal to n phi. The flux linkage is given by flux into number of turns. Flux linkage lambda equal to n phi. If the medium surrounding the coil is linear, then lambda is proportional to I. If the medium surrounding the coil, ఈ కాయిల్ చుట్టూ మీడియం ఏదైనా లీనియర్ మీడియం ఉంటే ఎయిర్ కానీ ఏదైనా lambda is proportional to coil. Flux linkage is proportional to current. Flux linkage is proportional to current. Therefore, psi lambda equal to Li or inductance or self-inductance. L equal to psi lambda by I, where lambda is known as n phi by I. Lambda n phi by I. L equal to inductance also defined as flux linkage, ratio of flux linkage n phi to current flowing in the same coil. That is inductance. Self-inductance is defined as, simple formula is L equal to n phi by I or lambda by I. That we have to remember. What is self-inductance? Self-inductance also defined as the ratio of flux linkage divided by current, n phi by I Henry. Self-inductance is, inductance means self-inductance, L measured in Henry. Inductance always measured in Henrys. Self-inductance, therefore we can define, self-inductance is defined as the flux linkage per unit current. That is, flux linkage is lambda and unit current you can consider flux linkage per unit current due to current of same coil. That is meant by, that is the important thing. Self-inductance is due to same current of the same coil. Mutual inductance is opposite current. Opposite coil current induces inductance on another coil, that is known as mutual inductance. Mutual inductance. Now go for mutual inductance now. What is mutual inductance? Already you studied previously. Again remember that. It is defined as the ratio of flux linkage of one coil in one coil, flux linkage with one coil due to current flow in another coil. Due to current flow in second coil I2, assume that two coils we are connected. V1 is the supply for one coil, current I1 is flowing in the coil 1. Coil 2 is supplied with V2, coil 2 it is. Now due to current I2, a flux phi 2 is producing. Mutual inductance of coil 1 due to coil 2, that is M12. కాయిల్ 1లో ఉండే మ్యూచువల్ ఇండక్టెన్స్ అంతా ఈ కాయిల్ వల్ల వచ్చేది. అంటే M1 ఈజ్ ద మ్యూచువల్ ఇండక్టెన్స్ ఆఫ్ కాయిల్ 1 డ్యూ టు కాయిల్ 2 M12, దట్ ఈస్ psi12 lambda12 by I2, lambda12 by I2, that equal to N1 phi12 by I2, N1 phi12 by I2. సిమిలర్లీ మ్యూచువల్ ఇండక్టెన్స్ ఆఫ్ కాయిల్ 2, కాయిల్ 2లో ఎంత మ్యూచువల్ ఇండక్టెన్స్ ఉంటుందంటే ఫ్లక్స్ లింకేజెస్ అంటే N2 phi21, flux due to coil 1, where phi12 is flux passing through the coil 1 due to current in coil 2, phi12 is. Similarly, phi 2 1 is the flux passing through the coil 2 due to current in coil 1. Due to current in coil 1, that is I1. You can define now mutual inductance of coil 1, coil 2. M21 is lambda 21 by I1. Lambda 21 is flux linkages in coil 2 with flux in coil 1. N2 phi 21 divided by I. ఇక్కడ గుర్తుపెట్టుకోవాల్సింది ఏమంటే మ్యూచువల్ ఇండక్టెన్స్ అంటే ఒక కాయిల్లో ఉండే ఇండక్టెన్స్ ప్రొడ్యూస్ అయ్యే ఇండక్టెన్స్ డ్యూ టు కరెంట్ ఫ్లో ఇన్ అనదర్ కాయిల్. కరెంట్ ఎప్పుడైతే ఫ్లో అవుతుంది ఇక్కడ అనదర్ కాయిల్లో ఫ్లక్స్ ప్రొడ్యూస్ అవుతుంది ఖచ్చితంగా. ఆ ఫ్లక్స్ లింక్ అవ్వడం వల్ల వచ్చే ఇండక్టెన్స్. అదే సేమ్ కాయిల్ కరెంట్ అంటే సెల్ఫ్ ఇండక్టెన్స్ అవుతుంది. క్లియర్లీ వీ హ్యావ్ టు అబ్జర్వ్ దిస్. Mutual inductance of coil 1 due to coil 2, that is M1 is the mutual inductance. 2 stands for mutual inductance of second due to coil 2, that is lambda 12 by I2. Lambda 12 is N1 phi 12. Phi 12, that is the phi 12 is the flux link with the coil 1 due to coil 2. Second suffix is due to another coil. Similarly, mutual inductance due to mutual inductance of coil 2 due to coil 1 is M21 equal to lambda 21 by I1, that is N2 phi 21 by I1. M2 means mutual inductance of coil 2, but current we will consider will be coil 1 current will be considered. Coil 1 current will be considered. Similarly, mutual inductance of coil 1 means coil 2 current will be considered, because based on coil 2 current only mutual inductance will producing in this coil. Now what is phi 1 2 phi 2 1 phi 2 1? What is phi 1 2 phi 2 1? We can see now. Lambda 12 is the flux linkage of coil 1 due to flow of current in coil 2. Now we go for coefficient of coupling between two circuits. Coefficient of coupling means K, that coefficient of coupling between two circuits. When two magnetic circuits are kept closed together, now the two magnetic circuits are kept closed together, each other interacts with each other magnetically through flux linkages in the circuit due to current in another circuit. Then circuits are called magnetically coupled circuits. When two circuits are magnetically coupled circuit, when we can say this flux links with this flux and this flux will be links with this flux. This is the phi 1, this is the phi 2 previously assumed. This flux links with this one, then it is a magnetically coupled circuit. The coefficient of coupling we already know K equal to M by mutual inductance divided by square root of L1 L2, where L1 and L2 are self-inductances of two circuits, where M equal to M12 equal to M21. This is the coefficient of coupling. K is called coefficient of coupling, or mutual inductance M is given by K into square root of L1 L2. For this derivation, lot of derivation already you studied previously. When two magnetic circuits are in series aiding, what is the opposing formula? In electromagnetics, the mutual inductance between two magnetic circuits M equal to K into square root of L1 L2, where K is known as coefficient of coupling. We can call it. The K is given by K equal to M by L1 and L2, where L1 and L2 are self-inductances. Self-inductances means what is the formula? L1 equal to lambda 1 by I1, self-inductance. At is mutual inductance means another current will come, I2. Due to this current I2, what is the mutual inductance? M1, 2. That we have to remember. And again, when two magnetic circuits are coupled together in series, suppose the two magnetic circuits are coupled in series, what is the inductance, that is equivalent inductance or mutual inductance between them, the effective inductance of the system is given by, suppose L1 is the inductance, L2 is another coil inductance. When two magnetic circuits are coupled together in series aiding, what is series aiding, what is series opposing? The flux in this coil and this coil are same direction, phi 1 and phi 2, the same direction. In the same direction sense, like this we can represent phi 1 and phi 2, two fluxes. Then what is the effective inductance or equivalent inductance? L equivalent equal to L1 plus L2 plus 2M, where M is known as mutual inductance. How to calculate M? Again, already told you, M equal to K into L1 L2. Similarly, when two magnetic circuits with inductances L1 and L2 are magnetically coupled in series opposing, here we have to remember it is series opposing. When the two magnetic circuits are connected in series opposing means it is the flux in this coil phi 2 opposing this. L equivalent will be, the basics already we studied previously in electrical circuits. The same again we have to remember for magnetostatics or electric potential. Third and fourth both are similar. Third unit is magnetostatics, L1 plus L2 minus 2M when opposing, L equivalent on opposing in nature. When two magnetic circuits with inductances L1 and L2 are coupled together series opposing, then effective inductance will be, series opposing means flux will be, then effective inductance of the system, that is L equivalent or equivalent inductance is L1 plus L2 minus 2M. Here minus will come, the minus is opposing, plus for aiding. When another formula we have to remember is, based on these formulas also you will get more questions, numerical problems they will ask in examination. When two magnetic circuits with inductance L1 and L2 are coupled magnetically in parallel aiding means L equivalent equal to parallelly aiding. Suppose two magnetic circuits in parallelly aiding, then if you connect like this, the dot mark indicates it is connected parallel aiding. L equivalent equal to inductance in parallel, L1 L2 minus M square divided by L1 plus L2 minus 2M. This is the parallel aiding inductance. When two magnetic circuits inductances are coupled magnetically in parallel opposing, if you connect like this, parallel opposing, this flux is in this direction, this flux is in this direction, then what we have to remember is plus, here only plus it is. This is about self and mutual inductances. Okay, now we go for another scalar magnetic potential, vector magnetic potential, and inductances are over. Now we go for numerical problems on scalar and vector inductances. A vector magnetic potential A bar due to a direct current in a free space is given by A bar equal to x square plus y square. AZ it is microweber per meter. Vector magnetic potential unit are Weber per meter or microweber per meter or milliweber per meter or like that. The vector magnetic potential is given by one equation, x square plus y square AZ. Determine magnetic field produced by current element at 1, 2, 3. Simple problem, this one. Okay, from that we can say that A bar equal to given data is A bar, scalar vector magnetic potential is given by A bar equal to x square plus y square AZ direction it is. At 1, 2, 3, what is B bar or H bar? That we have to calculate. B bar equal to del cross A. The curl of vector magnetic potential gives flux density. That equal to curl of that we are substituting. It is micro, hence we can go for 10 power minus 6 into curl of that one means determinant we are considering AX, AY, AZ, AX, AY, AZ, dou A by dou X, dou by dou Y, dou by dou Z, HX, HY, HZ. They are given that HX, HY are 0, 0, HZ is x square plus y square. By doing this magnitude of this determinant, we are calculating the magnitude. How to calculate magnitude already I told you. by taking on row and column, then we have to multiply this and this. After getting this, 10 power minus 6 2yax minus 2xay, that will be. Therefore b bar at 1 2 3 we have to calculate. We have to substitute in place of x 1, y equal to 2, z equal to 3. Substitute చేస్తే ఏమవుతుంది, y ప్లేస్లో 2 పెట్టారు because they given y equal to 2 and x ప్లేస్లో 1 substitute చేస్తే you will get b bar equal to 1 vector. If you want magnitude, then we can substitute. We can use formula magnitude of vector 4 square plus 2 square, that is the magnitude, into 10 power minus 6. Micro means it is 10 power minus 6. Suppose if you want to calculate h bar equal to b by b. Already we calculated b by mu. H bar equal to b by mu equal to mu naught mu r. Mu naught is 4 pi into 10 power minus 7. We can substitute here. Therefore h bar equal to, we can calculate if you know b bar. Everybody knows that how to calculate h bar. If you know b equal to mu h. Therefore h bar equal to 3.18 ax minus 1.59 to ay, amperes per meter, that is h bar. Find the self-inductance of a solenoid having 500 turns. Magnetic mean diagram of L equal to 5 meters. Self-inductance of solenoid. A solenoid means when a cylinder or any coil, if you wound on a rod or any cylinder, hollow cylinder, it is a solenoid. The number of turns are 500. The number of turns are 500. Area of cross section of the solenoid is pi r square. 22 by 7 you can use pi instead of pi. R square is 0.05. They given that L equal to 5 centimeter. We are converting into meter, that is 0.05 meter. D equal to 10 centimeter. Diameter is 10 centimeter. We can calculate R equal to 5 centimeter. R equal to 0.05 meter. Therefore L equal to, suppose we have length of the solenoid. Suppose they have length of the solenoid and that derivation. This problem we are doing with the derivation. Actually it is a derivation. This problem we are going to do with the derivation. Suppose we have long solenoid, then consist of n loops, then b equal to mu naught ni by l. Already we know that h equal to ni by l. That is the solenoid formula, h bar equal to. If you want to b, you can substitute here, h equal to ni by l. Mu naught into h, it is h ni by l. Therefore inductance of solenoid L equal to, how to calculate m? Phi m equal to b into a. Phi equal to ba, you know formula, b equal to phi by a. Therefore ba equal to, b is mu naught ni by l into a cross section. Therefore inductance means L equal to lambda by I or L equal to mu naught n square a by L. It is a formula for solenoid. L equal to n into mu naught nia by IL. From finally we get mu naught n square a by L. Therefore inductance of solenoid is 4 pi into 10 power minus 7 mu naught n square a by L we substituted. L equal to n phi by I, lambda by I similarly. It is the formula and derivation numerical problem also we substituted directly. Finally we got the answer L equal to 0.049 henries or millihenries means 49 millihenries it is. We can use another formula, self-inductance of a solenoid, that is ampere circuit law. We can use H dot dl equal to I. Consider a solenoid of carrying a current I. Assume that solenoid it is n number of turns. A current is flowing is I. I is the current flowing in this solenoid. The total flux produced due to current 5 Webers. Assume that 5 is the Webers that flux produced by this current. Due to number of turns, due to flux current flow in coil, L is the length of the solenoid, A is the cross section of area of solenoid. By ampere circuit law, what we can say, H dot dl equal to I. Line integral of H dot dl equal to total current enclosed. By using ampere circuit law also we can calculate simply. What is the inductance of a solenoid? H dot dl equal to I by using ampere circuit law it is, where I equal to total current. H integral dl equal to I. If you integrate dl, then what we will get? Total length L. HL equal to Ni. Therefore, H bar equal to Ni by L. H bar equal to Ni by L, already we know this formula. Since B equal to mu H, that is formula for calculating B, we are substituting in place of H, Hi equal to Ni by L. H equal to Ni by L, we are substituting. Finally, B equal to mu naught mu r Ni by L. Mu naught mu r Ni by L, that we obtained previously. Therefore, B equal to phi by A, phi equal to Ba, everybody knows that. Flux density equal to B equal to phi by A. From this equation, phi equal to Ba, phi equal to mu naught mu r Ni by Al. Previously what we substituted. We know that self-inductance L equal to N phi by or lambda by I. L equal to, substituting that, L equal to mu naught mu r N square A by L. That is the self-inductance of solenoid. Self-inductance of solenoid it is. Similarly, we can use Biot-Savart's law, ampere circuit law, find self-inductance of a toroid. Self-inductance of a toroid. What is toroid? If the coil is wound on this cylinder, then it is a solenoid. If the cylinder is in the form circular, it is a toroid. It is a toroid. Same principle we are applying. But toroid having radius r, cylinder having radius r. The radius of the toroid from the center, we have to consider n number of turns are there, n number of turns are provided, I current is flowing. Let n equal to number of turns on toroid, r is the radius of the toroid, it is the r from the center. What is the radius? R. By ampere circuit law, again we are applying how to calculate inductance. See, we can see simply H dot dl equal to I. H dot dl equal to I. Therefore, what we did previously, integration of dl means L, total length will come. Total length will come. Integration of dl is L and I equal to Ni, total current. Total current means number of turns also will consider Ni, we can substitute. We can substitute Ni. Where L is known as 2 pi r, perimeter of the toroid. H equal to Ni by L. From that, again we can substitute phi equal to B by A. Similarly, what we substituted, finally we got L equal to lambda by L equal to lambda by, finally we got the equation mu naught mu r N square A by L. L is known as perimeter, 2 pi r we have to substitute. The same formula we applied for solenoid and toroid, but L is the perimeter. L is the perimeter, 2 pi r we have to consider. Similarly, we go for mutual inductance between two straight wire and square loop. That is also important. Mutual inductance between straight wire and square loop. Mutual inductance ante telusu meeku already. Mutual inductance ante oka coil lo poye current valla vache inductance, another coil lo vache inductance. Now consider a straight conductor. Oka straight conductor ni మనం కార్టేషియన్ కోఆర్డినేట్ సిస్టంలో అనుకుంటే ఒక స్ట్రైట్ కండక్టర్, current flow through this conductor is I1. The straight conductor is placed at origin along y-axis. Magnetic field intensity due to long straight conductor is given by H equal to I by 2 pi x. H equal to I by 2 pi x at a distance x equal to A. X equal to A plus D. Assume that it is D of a surface area. Consider a straight conductor and a square loop. రెండు ఒకేసారి కన్సిడర్ చేసుకుంటున్నాం. మ్యూచువల్ ఇండక్టెన్స్ ఈ రెండింటి మధ్య ఎలా ఉంటుంది? మ్యూచువల్ ఇండక్టెన్స్ బిట్వీన్ స్ట్రైట్ వైర్ అండ్ స్క్వేర్ లూప్. ఒక స్ట్రైట్ కండక్టర్ అండ్ స్క్వేర్ లూప్ హ్యావింగ్ x equal to A and A plus D. The diameter is D, square loop side is D, A plus D we will get, and y equal to D, it is y-axis, it is along x-axis it is placed, it is y equal to D. It will become magnetic field intensity due to long straight conductor is H bar equal to I by 2 pi x. Since B equal to mu H, you know that B equal to mu I by 2 pi x. Since B equal to mu I by 2 pi x, Magnetic flux linkage of square loop is yes, lambda equal to n phi. Magnetic flux linkage of square loop. Where since n equal to number of 1 turn, assume that square loop is S2 and carrying conductor is straight conductor is S1, assume that. Magnetic flux linkage of square loop is lambda equal to n phi, where n equal to 1, hence it is known as yes, lambda equal to phi. Will get lambda equal to phi equal to surface integral b dot ds2, surface integral b dot ds2. We know that phi and b relation. Phi is obtained by integrating flux density with respect to surface, that equal to lambda equal to phi equal to a to b integral a to d, a to a plus d, and b is already we know that flux density mu I1 by 2 pi x dx dy, lambda equal to mu I1 by 2 pi x. The integration we are carried out. Finally, we have to get the answer. Therefore, mutual inductance is m equal to lambda by I1, that equal to m equal to mu d log 1 plus d by a. The mutual inductance is the simple derivation. It is also very important derivation for exam point of view. It is mutual inductance due to a straight wire and a conductor, loop conductor.